Now let's consider the scenario where we can't assume that we're working with independent random samples. In particular, we're going to do what's called a paired samples test for the difference of means anytime we're working with dependent random samples. And again, an example of that might be if we're talking about a weight loss program where we want to compare the before weights with the after weights to see if there's a change. It would only make sense to pair the before weight for a person with their own after weight. Otherwise, you won't get a very good comparison if you're comparing the before weight for, say, Mary with the after weight for John. So in this case, when we're looking at dependent random samples of size n, we're either going to need to assume that we're working with normal differences or large samples. And depending upon the size of our sample, we can either use a z-test or a t-test. And I'll get to that in just a second, and I'll also explain what normal differences are in a moment. Now, the null and alternative hypotheses for this type of test are defined the same as with the other tests for the differences of two means, mu1 minus mu2. So I'm not going to revisit all that here. Likewise, our critical regions will be constructed similarly for the left-tailed, right-tailed, and two-tailed test, whether it's a z-test or a t-test. The only difference will be that if it's a t-test, we'll use a different number of degrees of freedom than we did with the pooled samples t-test. The next step when we're doing a paired samples test is we have to calculate differences. So that means we're going to go and pair up before scores and after scores, for example, if we're talking about our weight loss program, and we'll calculate the difference between the before and the after for each individual in our sample. And in the case where it's not a before versus an after, we'll do the same kind of thing. We'll just pair for each sample item. We'll compare the values for the first sample and take their difference, compare the values for the second sample, take their difference. Then we get a list of new values, di, where I ranges from 1 to n, and for those values we'll need to compute the sample mean, and we'll also need to compute the sample standard deviation. So if we revisit our assumptions, that second assumption that we're working with normal differences, meaning that we were looking at this di random variable, and if it turns out that it has a normal distribution, then we can make use of the appropriate test. Or if we don't have a normal distribution for the di variable, then we hope that we at least have large samples. Now let's talk about the test statistic. If we're in the scenario where we have a small sample, then we're going to assume we're working with normal differences, and we'll compute a t-score for our test statistic by taking the d-bar variable and subtracting the hypothesized difference between the two means, divide by the ratio of the standard deviation for the d variable and the square root of n. And we'll do that t-score with n minus 1 degrees of freedom. That means that any critical region we do associated with this test would have to be constructed using the t-distribution with n minus 1 degrees of freedom. In contrast to that, if it turns out that our samples are large enough, then again we can essentially think about making use of the central limit theorem that would allow us to say that the di variable is approximated by a normal distribution, and therefore we can compute a z-score when standardizing the d-bar by doing d-bar minus the hypothesized value of the difference of the two means divided by the ratio of the standard deviation for d and the square root of n. Now, it's also worth noting, we didn't cover this in Chapter 11 when we were doing confidence intervals, but everything that we've discussed here in this t-test procedure for paired samples could be applied to creating a confidence interval for paired samples. We would just take the d-bar value, add and subtract a critical value that for t with alpha over 2 area in each tail for n minus 1 degrees of freedom, and then multiply by the standard error for the d variable, and we would get a nice confidence interval for paired samples. So you should add that to your list of confidence intervals now that we can generate. Now let's look at an example for dependent samples. Well, suppose that my friend Frida is a nutritionist and that she's been working towards developing an effective weight loss program. And below we've got the weights of 10 subjects before and after implementing her experimental weight loss program. And the way you want to think of this is that when you look at that first column where the before weight is 156 and the after weight is 147, those measurements come from the same person included in her weight loss program. Likewise, the second column gives you the before and the after weights for a different person in the program, but they're definitely pairing the before and the after weights for the same individuals. So our question is there evidence at the 10% significance level to suggest that Frida's weight loss program is effective? To start, we'll acknowledge that we have dependent random samples, so we're working with a paired samples test. And in this case, since we have small samples, we're going to assume that the differences are normally distributed, in which case we'll be doing the paired samples t-test. Then the next thing we have to do is calculate the differences. So we'll look at the paired values and calculate the difference for each pair. In particular, what I've done here is I've just added an extra row to the table, and in that row I've done the before weight minus the after weight, and I get the following values, which I can then use to compute the mean, d bar equal to 2.4, and the sample standard deviation equal to 6.26. Then we'll define our null hypothesis to be that the mean for the before weight is the same as the mean for the after weight, and the alternative would be that the before weight is greater than the after weight, because then that would mean my weight loss program is effective, right, if the after weight is less. So that tells us that we're working with a right-tailed test. Since we're doing a right-tailed test and we know that this is a t-test, then to construct our rejection region we need to identify alpha, which is 0.10, and our degrees of freedom is 1 less than our sample size, so 10 minus 1 gives us 9. We're looking for a critical value then, which has an area of 0.1 in the tail and 9 degrees of freedom. We can find that right off of our t-table. That's 1.383. So our rejection region then is the set of t-values where t is greater than or equal to 1.383. And now our test statistic will be a t-score, since we are doing a t-test here for our paired samples hypothesis test. So we'll look at the difference between the d-bar value and the hypothesized value of the difference between the means from our null hypothesis, and divide that by the ratio of the sample standard deviation and the square root of the sample size. If we do, we get a t-score of 1.21. When we compare that then to our rejection region, which said that t was greater than or equal to 1.383, we see that our test statistic does not lie in the rejection region, so we will fail to reject the null hypothesis. As such, that means we're going to conclude that there is insufficient evidence to suggest that the weight loss program is effective at the 10% significance level. It's worth noting at this point that, much like with confidence intervals, there's still one scenario that we really haven't considered when we're talking about the difference of means between two independent samples, and that would be, what if we can't assume when we have independent random samples that we have equal variances? So what if sigma 1 squared doesn't equal sigma 2 squared? Well, there are some options that exist. One option that's not mentioned in this book is called a non-pooled test, and the non-pooled test involves a slightly modified test statistic, and it also involves a more complicated formula for your degrees of freedom. That can be found in other statistics texts that are available out there, but it's not in this book, so we're not really covering it at this stage. Likewise, another option would be to randomly pair values from the two samples, treat their differences as a random sample of size n, where n is defined to be the minimum of the two sample sizes from our independent random samples, and then define our null hypothesis to be that mu is equal to delta, and use an appropriate technique for a one sample test. So it would seem almost like a combination of the paired samples test and the pooled samples test, in the sense that you're using some of the notions from the pooled test, but you're also coming up with paired differences from the paired test. But in this case, we're randomly pairing differences. And this is possible, but we probably won't be doing that at all. So if you should happen to read in your textbook and you see some paragraph that describes this, you can just keep that in mind.